the nth Fibonacci number iteratively versus I had a recursive algorithm that is to compute the nth Fibonacci number recursively. Can you tell me which one of them would be faster in a sense?
Can you say that again? You're trying to figure out the Fibonacci sequence. One is recursive and the other one's what?
Yes, other one is iterative in a loop, basically. So Fibonacci, so let's say nth Fibonacci number, I give you the n. So if you have iterative versus recursive, which one of it do you guys think would be faster?
And so iterative is starting from the beginning and just going down the line, right?
Yes, yes.
And so can you describe recursive in like a snippet?
Recursive would be int n, where you have return fib of n minus 1 plus fib of n minus 2 with the base case of n equals 1, then you return 0. Yes, calling the function again and again is recursive. So Brian says that theoretically they can run in the same time, but is that correct? Why? Yes, something. I don't need an answer for iterative versus recursive. I need an answer as to why you think it is iterative or recursive. Because usually whenever we talk about recursive algorithms, merge sort, quick sort, or whatever searching algorithms, usually the complexity tends to become n log n in case of sorting, right? We know about bubble sort, insertion sort, and those algorithms, and they usually take n squared time. But whenever we had, recursive calls, they somehow tend to become n log n complexities. But is it a fact that using recursive calls is the thing that is making it n log n, or is it the fact that it is making some good choices about those problems that is why it becomes n log n? So as Vamsi says here, recursive calls gets you more and more redundant recursive calls, and an iterative call might not require that redundancy. So let me give you an example for the Fibonacci thing. So let's say that I'm trying to find out the let's do fourth Fibonacci number, right? So in order to find the fourth Fibonacci number, I need to know the third Fibonacci number and the second Fibonacci, right? In that situation, I first need to find out what is the third Fibonacci number. Fine, I have not computed that yet. So I need to find out for the third Fibonacci number, I need to find out the second Fibonacci number plus the first Fibonacci number, right? For this, I again need to find out the second Fibonacci number. In that case, that is fine. I have not computed that yet. Second Fibonacci number is f of 1 plus f of 0, but that is going to be 1, right? No, f of 1 plus f of 0, both. Just change this code a bit.
Well, sir, so in this particular case, is there any equation that defines the Fibonacci where you could shortcut it and jump to whatever?
Yep, there is. And there is an entire segment of our class that will talk about this. This is going to be called dynamic programming. So before we go into that, but there is also another way that is called memoization. So not memorization, memoization. So we'll talk about that later. Okay. But primitive low, so it does not. Yes, MS tail recursion will degrade it to a loop, but that does not mean that you're not making redundant calls, because it is tail recursion, yes, but the fact that you're calling your function twice within your function, fib of n minus 1 and fib of n minus 2. In that situation, some redundancy pops in, because now once you have f of 4, f of 3 plus 2 and blah, 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 all of those things, now we have computed f of 3, but now we also need to compute f of 2, right? So for this, so we have f of 2 equals to 2. So we have this as 2, we have this as 1. So that results in, oh, sorry, this is 1, my bad. because 0 is, this is 1, f of 2 plus f of 1 is going to be 1 plus 1, that is going to be 2. And then finally f of 3 plus f of 2 is going to be something, but we know what f of 3 is. F of 3 is going to be 2 plus something. But now we need to recompute f of 2 because we did not save it anywhere, right? So in order to find f of 2, we again need to find f of 1 and f of 0, right? And you can see that this is f of 2 and that becomes trivial. But if this was a large enough number, we would have to again go through the entire tree, maybe compute many things redundantly again and again over time. And that is where some recursive functions might not take the same amount of time as iterative functions, and some iterative functions might be faster than recursive solutions. Does that make sense? Sort of. As long as you're not recomputing the same thing in your recursive tree, you are fine. Same as merge sort. Merge sort does not recompute something redundantly, right? Again and again. It is doing separate things. But since the Fibonacci sequence requires a shared sort of tree, it has a redundancy built into it in this particular
algorithm. Essentially the redundancy is recomputing f of n minus 1.
Yes, essentially. But in a tree fashion. So if there was a way where we could have saved the values that we have already pre-computed, so if there was a way where we could have saved f of 1, f of 2, f of 3 somewhere, then whenever we required f of 2 again, we can just query that value with a big O of 1 complexity. Then we would not have to go through this tree again. But since we need it, that becomes redundant. Make sense?
And so this is, yes, this is where we get into like the golden mean and things like that.
The golden mean as in?
It's the calculation for Fibonacci.
Oh, the golden ratio, are you talking about?
Right, golden ratio, whatever, where it's like something over square root of 5. And so that way, I just wanted to answer the question. If you use that shortcut, then recursive would definitely be quicker, right?
Yes, if you use that shortcut, then recursive is quicker, but that fails the purpose of your recursive function, right? So if you want to save it somewhere, then you would need to lug around the entire saved array over all function calls, or you can make it a global variable. But if you make it a global variable, that contradicts the condition for a recursive problem, right? A recursive algorithm needs to have self-contained. So there are those things too, but we are not bothered about code efficiency. We are bothered about analyzing those things. So essentially that is something.
Okay, cool. Thank you.
Yes, welcome. Okay, so that is divide and conquer in essence. Let's just move forward. So let's talk about merge sort. We all know what merge sort is. I will still review it, but is there anyone who does not know how merge sort works? Or
I do not, sir. Like, but
okay.
I think I understand it, but I don't know.
I have a review about it, but I was just wanted to. Yeah, that's fine. So
I think I understand it, but just not by its official name.
Okay, perfect. Okay. Anybody else? Don't be shy, but anyway, okay, good. So merge sort is a sorting algorithm that would take an array of size n and recursively sort that array. So what it does is essentially, forget about the if case for now. It recursively, so essentially it breaks that array into two halves, two equal halves, where the first array is all the numbers from index 1 to index half, n by 2, and the other array becomes index n by 2 plus 1 to n. So essentially breaks it in half and then says that, okay, in order to sort this entire array, sort this half and sort this half separately and then merge them together, right? And then the base case of this is if my array just has the single element, then that particular element is always sorted, right? Okay. So there are two components here. The dividing part here is when we divide the array into two halves. The combining part here is when we are merging those two sorted arrays into a single array. Okay. So this would be the pseudocode for merge sort, but it is pretty much the same thing as earlier. So if so in this case, your merge sort algorithm takes in three arguments: the array, the starting location, and the end location of your array. Because essentially we are going to break it down into smaller and smaller components. So each recursive call needs to know its part of the array that it's going to work. And then while they are not overlapping, so left hand side and right hand side are not overlapping, you essentially compute the midpoint of your array, sort the first half of your array using merge sort APQ, that is A start midpoint, sort the second half of your array, that is AQ plus 1R, that is A midpoint to end, and then basically you need to merge all of them together into a single array again. So the merging sequence essentially means that you, let's say, you broke down the array into smaller and smaller components until you get a single element everywhere. So if you look at this particular area, all of these elements here are technically sorted because the subproblems only contain a single element. Now, while merging them back, we are going to look at individual elements and merge them in order. So once we merge 5 and 2, and I'm going to talk about this too. So once we merge 5 and 2, it becomes 2, 5. We merge 4, 7 to get 4, 7. And then we have this larger array, 2, 5 and 4, 7. Same thing for these arrays as well, but you can just infer that. Now we have to merge 2, 5 and 4, 7, and it merges it together to get 2, 4, 5, 7. So you see that you can't just concatenate those two arrays. If I had concatenated them, it would have been 2, 5, 4, 7. But instead I have to do it as 2, then 4, then 5, then 7, right? And then finally the same process applies, and then I get the final larger array. Okay. So it's just talking about the same thing. So in essence, let's say that I have these two sorted subarrays, 20, 12, 13, 11, 7, 9, and 2 and 1. So first I would check, first I would get 1, then I would get 2, then I would get 7, then 9, then 11, then 13, and then 12 and 20. Okay, so how it does this is you have your two arrays. It compares the first two elements of your array. Remember that your arrays or your sub-arrays are internally sorted. So we have this sorted procedure, that is 2, 7, 13, 20 is sorted, 1, 9, 11, 12 is sorted, right? So in that case, if I just compare the first two elements of my array, I'm comparing the smallest elements of both arrays, right? So comparing 1 and 2, we get 1. Now we compare between, so 1 is done, so we compare between 2 and 9. So we compare 2 and 9, we get 2. Then we compare 7 and 9, we get 7. Then we compare 13 and 9 to get 9. Then we compare 13 and 11 to get 11. And then we again continue the process for 13 and 12 to get 12 and so on. Then we get 13, then we get 20. And that is how we get your sorted array. So the code for this is essentially, first, what we usually do is we first copy the two arrays into two new arrays, left array and a right array. And then what we are trying to do is comparing it each time and then adding it back together into the original array. So let me visualize this code, and then you guys can go through this code on your own time. Okay. So how clear is this image here? I can zoom it in.
I can see it.
Anybody having trouble? Okay. Okay, so
now I can really see it.
Okay. So think